my screen. Can you see it?
Yes.
Okay.
Also, last week's text file was not yet uploaded to the Teams files.
Sorry, I will do it now.
Okay.
Okay, thanks. Okay. Okay, so we okay, so for this week, the plan was to talk about metatheoretic properties of type theory, and in particular canonicity. But in fact, we already talked about some. So what is a metatheoretic property? It's type theory is some kind of formal theory, and metatheoretic property is something that you can state about the formal theory. So a non-metatheoretic thing is something that you can prove inside the theory. It's something that you can use the theory for. And metatheoretic is when you go outside of type theory and you prove something about it. I think I've already started it, no?
It seems that's not the case.
Yes, there is a red dot in the corner. I see it.
I can see a button stop recording.
I don't see the recording going.
I see Kaposi Ambrus started recording and there's a red button in the corner.
It's not the case here.
Same here.
Okay,
Yay
I
for
don't know.
Teams consistency.
It's some problem with Teams, probably.
Okay.
Okay, and in fact, in this series of seminars, we didn't really talk about. We mainly talked about metatheoretic stuff. So, I mean, that's why the name of the seminar was metatheory seminar, anyway. But so we prove metatheoretic properties like consistency using the standard model. So this meant that there is no term in the empty context of type bottom. And then there is no, how do you state this, like this maybe? There's no term in the empty context of type bottom. We talked about parametricity. For example, one consequence of parametricity was that if we have a term in the empty context of type for all A, AROA, and we know that this term is equal to the identity function. Which is just, I don't know, maybe how did we write it, like lum q or something like this.
But we didn't have this exact parametricity, but instead a slightly different version.
Mm-hmm.
Very.
Yeah, but did we prove this?
No.
Did we prove this statement or no?
No, what we proved is that the standard semantics of T is the identity function.
Oh yeah. Mm-hmm. Okay, but we could have proved this, but we proved something complicated.
We could only prove this version with a different model.
Mm-hmm. Mm-hmm.
Like a symplectic parametricity.
I mean, we proved that, yeah. But we also proved things like whenever we showed that the models justify something, we know that that thing is consistent with the theory. For example, this thing, this statement here, because this was true, this statement in the standard model, then we know that this can be assumed because there's a model for it. And then we talked about other things like, it's also consistent to assume that you have an operation which turns a context into a type, like constant types. This is something that is also consistent because you have a model, or or function extensionality. I don't think we talked a lot about function extensionality, but so if you have a term that in some, write it like in some x in A, we know that there's an identity between fx and gx. For any x in A, then we have that there's an identity of functions of the function type of f and g. There's a model where this statement is true. This we mentioned this, the setoid model. We haven't talked about this, but this is fine. We also maybe this is a, and then another metatheoretic property was, for example, UIP, uniqueness of identity proofs. So these are all things that we do not inside of type theory, but we state them about models of type theory, or we state them about the initial model, which is the syntax. So statements about the model of type theory, or statement about the if something is true, if something is true for the syntax or the initial model, then it is true in every model, right? So statements about the syntax. And usually when you whenever we have something which holds in the model, I mean, for example, when we have this so for example, consistency, we went through the standard model. So in the standard model, the interpretation of the empty type is the metatheoretic empty type. So if there was such a term in the syntax, right, then we could interpret it as the metatheoretic empty set. So it cannot exist, and this is how we used a model to say something about the syntax. So so there are other important properties of the syntax which are some kind of most important property of the syntax. It's usually called normalization. And in fact, some of these, for example, consistency and parametricity, are closely related to this normalization. And you probably have heard about normalization in the context of the lambda calculus. And the setting of type theory is quite similar to the setting of the lambda calculus, and or simply type lambda calculus. And normalization is also about when we want to say that. So normalization is basically the statement that you can run any program. So any program can be run. If you have some term in type theory, some term gamma A, then you know that this term is equal to some t prime, and the t prime is equal to some t prime prime. And in the end, you get something called the normal form. So for example, if you have a program, I don't know, like a simple example is you have 3 plus 2, then you know that it is equal through some equalities. 3 plus 2 is 3 is suck 0. This is plus is some defined function, and 2 is suck 0. And now plus is defined by, usually it's defined by the using the recursion principle of natural numbers, and it's defined by recursion on this first argument. So you need to say, so basically it's this this thing, and now you can use the computation rule. So recursion, and this is the case for 0, this is the case for successor, and this is the argument that we recurse on. So, you know, this is the recursive definition here. Just to remind, the recursive definition is like this, that 0 plus n is equal to n. But in fact, in this case, this is concretely suc0. Then we return suc0. And in the case of successor of n, this plus function returns successor of n plus, and then this number, right? And this is encoded in this recursive definition, but then we can use the beta rules, so some equalities for this recursor, and then we get that this is the same as, for example, in one step, we get that we take off one sock and put a sock there instead, and then we get sock of rect not this and sock, but now not on this number, but one smaller number, right? And then in a few more steps, we get that we have 5 successors, right? And this is what is called a normal form. Because, so a normal form in rewriting theory is some kind of term to which no rewriting rule applies. So here I cannot rewrite it to anything else. Now for type theory, we just say that basically here is a normal form. It's something which cannot be simplified anymore. So in some sense, it's in a simpler form. And, you know, we can always make this term more complicated. Like this one is another term, which is a more complicated description of the same term, of an equal term. But this seems to be some kind of simpler thing, because you can read it off immediately that it is 5. While from this one, it is some complicated function and application and whatever. Okay. So, okay, so for type, so what are normal forms? Normal forms. So let me just, the specification is the following. We have some function normal form, which again from a context or NF and the tie, it gives us a set. And for example, normal form in the empty context of type natural number is simply a natural number. Or it's something equivalent to natural numbers, because this will be one property that we want, that if we have a natural number in the empty context, then, you know, this natural number could have been built using the recursion and lambda and application and lots of different operations, but we can always do the same thing that we did here. So we can always just rewrite that term through equalities and obtain a normal form. So, okay, so obtain a natural number. And here, so this not is a type in our object theory, and this n is a natural number in our meta theory, right? So you need to distinguish these two things. Okay, so this is how we want this NF to behave, that, for example, for the empty context and natural number, it should give us this. So note that if we are not in the empty context, then, you know, we might have a natural number here, and when we have such a term, for example, x is such a term, right? or if we use de Bruijn indices, then Q is such a term. It's a natural number. It's a natural number in this non-empty context, and this also cannot be simplified anymore. So if we are not in the empty context, or let's say we are in the context with only a natural number variable, then this 0 de Bruijn index can also be that's also a normal form. So you see that normal forms of natural numbers do not need to be necessarily natural numbers. Okay, and normalization is now given by a function. Okay, let's call it norm, which takes a Tm gamma A and gives you a normal form. Okay, we haven't specified what this NF is yet, but we saw some examples of how this NF would behave, and what normalization should do is go from terms to these normal forms. And maybe I slightly changed the definition of okay, and let me just say that I should have said already that we have a function sometimes called quote, which taken a normal form returns a term. Okay, so every normal form can be mapped back to a term. So for example, every natural number, right, metatheoretic natural number has a corresponding term, or 1 is successor of 0, and so on. Okay, so this is how this function, which goes back from normal forms to terms, works. Okay, and then this normalization, you could say that this normalization basically runs the program. From a term, it extracts a normal form, and it has two important properties. So one is that if you start with a term, you obtain a normal form, and then you quote it back to a term again. It should be equal to the original term. Okay, so that this normalization doesn't give you something. So this normalization respects the equalities. So you get something which is you get a normal form which is equal to the original term. Otherwise we could implement the normalization function. Like if we didn't have this property, we could just implement normalization by saying norm t should always be 0. Okay. Okay. This wouldn't work because the types wouldn't match. But maybe there is some other stupid way of implementing this norm function where the types match, but you always return. For example, for any natural number type, you always return 0 or something like that. That would. Okay, so for example, rules out normalization function for natural numbers with just NF gamma, which just does this, right? And this is called completeness of normalization. And then there's also another property, stability, which says the other way. So if we start with a normal form, let's call it n, then we can quote it back to a term, and then I can normalize it, and I want to get back the original normal form. Okay, so this says that there is no rubbish in normal forms. So everything that is in normal form is the image of something which is a term, right? And so before saying what normal forms are for type theory, I want to show some simpler examples of theories with normal forms. So examples. Wait, let me just this here. So example of normal form for simpler theories. Okay, so one example is integers. the theory is given by something like Z is a set, let's just call it Z is a set, and 0 is an integer, successor is takes an integer and gives you an integer. We also have predecessor, which from an integer returns another integer. But now we have too many things, so we need to say that if you take the successor of a predecessor, it is equal to the integer itself. Okay, and we have the other version as well, that if we take the predecessor of a successor, we get back the same thing. Okay, so this gives the theory of integers, or there are other ways to represent integers by pairs of natural numbers, but then you again need some kind of equality. Okay, and then the normal forms for integers, are given by an inductive type, which says that an integer is either a negative or a positive number or 0. So the normal form would just be, it's either a natural number or 0, okay, let's say top, or another natural number. Okay, so it's negative, 0, or positive. So for example, if we, so then normalization will take integer, okay, from the initial integer algebra. So maybe I write it I dot z because it's in the initial integer algebra, and then returns this. Okay, for example, if I normalize, I don't know, soc of pred of soc of 0, then I should get ing2, or I don't know, ing3. So this one of 1, right? Because this is the same as 1. This successor and predecessor cancels each other, and then we just have 1. Or if I normalize 0, then I get ing2 of pt. Yes?
Counting from 1 in the negative and positive versions, or from 0?
Oh yes, sorry, we should count from 0. Yes, that's right. We should count from 0. So 1 should be mapped to 0, right? Because 0 itself is mapped to the middle thing, right? And okay, let's write a negative number. So for example, pred of 0 will be mapped to ing1 of 1, right? Because it's -2. Okay, so this is -2. Just write it here. This is 0. This is +1, right? And so, and usually what we want from these normal forms is that they are somehow the simplest form of our terms. So in fact, here what we really want is that there is no such soc-pred situation. So all the soc-preds really canceled themselves, and this is how we force that they cancel themselves, that we separate these separate cases. Okay, and now it's quite nice, because if you have an integer in a normal form, if you have two, say, one thing that is hard to do with proper integers, and okay, so hard to do with proper integers and easy with normal forms is, for example, comparison for equality. So when you want to decide whether two integers are equal, then if you have these things, then it's very easy to decide whether two integers in normal form are equal. If they are both ing1s, then you compare the natural numbers. If they are both ing2s, then they are equal because they are both 0. If they are both ing3s, then you again compare the natural numbers, right? If one of them is an ing1, the other is an ing2, then there's no way that they will be equal, right? And so on. So this is an advantage of normal forms, that it for comparison for equality is is easy. But I mean, here in this very simple case, you might have asked, why didn't we define integers like this in the first place? So why do we define integers in this complicated way and not in this simple way? And there's an answer to that. So hard to do with normal forms and easy with integers is, for example, define addition or prove properties of integers. I mean, this is a very inconvenient language. Whenever you want to define a function, whenever you want to do anything, you always need to do case distinction, whether that thing is zero, non-zero, and so on. While here, you just need to give an algebra of this, and this has a very nice structure. And it's the same with type theory. So it's very easy it's nice. We always want to use lambda and application everywhere when we write type theoretic terms. And if we were forced to use normal forms, which we will see it will be some complicated and restricted language, it will be a similar comparison to integers like this and integers like this. Okay. Another example is another simpler theory is say what is the usual example is monoids over, let's say, free monoids over a set A. Okay, so let's say this theory, how do we write this? Let's call the theory M. So we have an M, which is a set. We have some inclusion. So from A, we can go to M. Then we have a unit of the monoid. And then we have I don't know, let's write a dot, which is the monoid operation. And we have left identity, right identity, and associativity, right? So I don't know, we know that unit times anything is the same as this, x times u is the same as this, and then we have some associativity, right? This is okay. This is the free monoid, and then the normal forms for this, normal forms. Can someone who didn't know this before guess what normal forms are? Or someone who, okay, I don't know, someone for who this is not completely trivial, what are normal forms in this theory? Okay, so normal, so yeah.
Sorry, I feel like I've already seen this before, but it's not completely trivial for me. But the first thing that comes to my mind is that we had to remove all the identities, so the u's will disappear unless the single element is the u.
Yeah. Yeah.
And then we convert all the associativities to one side, I guess.
Yeah. And then if you look at the structure, because you know the thing, so things here, these are trees, binary trees, where at the leaves you either have a U or an inclusion of A, right? But you also equate some of the trees, and you can always, every tree can be transformed into a normal form tree, which only branches to the right, and the left branches are always some inclusions. So from an arbitrary tree, you can always obtain a tree which looks like this. So there's always a binary operation here. Here you always use inclusion on the left, and on the right you always have a binary operation again. And here again, okay, the inclusion also has some child, whatever. And then here again you only have an inclusion, and here you have another binary operation, and so on, okay? And this ends, and on the left there are always inclusions, and in the end, this ends with it's with the last inclusion is like this, when you have an inclusion here, and here you have a unit, right? So every such tree in the free monoid, every such tree here can be equal to such a tree by iterated usage of these equations, and this is just the same as a list of A, right? So here the normal forms are just lists of A. So normalization goes from syntactic monoid over A, okay, so the I dot M to list of A, okay. And here again, if you think about what completeness and stability is, so obviously every list can be turned into such a tree, right? We just replace nil by U and cons by this thing, that the dot and the inclusion. And so if we have some term T, we normalize it, we get a list, okay, and then we include it, then we quote it back to have get a term, then we get the original term, and this states that that during this normalization, what we really did was we worked using these equalities, and that's how we obtained the T, okay. And if you think about what stability is, now if you have some excess, which is a list, and we quote it to become a normal form, and then we normalize it, we get back the same original list. This means that there is no list which is not in the image of this normalization, right? So because if we had such a list, then we would obtain something different, right? So I just write it here again. So this is completeness, and this is stability. Okay. So these were two simple theories, integers and free monoids, or monoids over A, where so the free monoid is usually called the free monoid over A is the initial such model, right, of this theory. Okay, that's a different name for the same thing. Okay, so what are normal forms for type theory? So maybe first I say what are first informally for a type theory with only I don't know, function space. Yeah, only function space. That's already and okay, we need some base type, because if we only have function space, we can't start from anything. So let's say function space and bool. Okay. So normal forms are given mutually. So we say we have something called neutral terms, and we have normal forms. Okay, and for the neutral terms I write n, and for normal forms I write v. And I present it with BNF grammar. So a neutral term is either a variable or a neutral term applied to a normal form. Okay, or because we have this bool here, or we can do the eliminator for bool is if then else. So if we apply if then else on a neutral term, then I cannot apply any computation rule here, right? So I don't know what to do with this n, because look, these are the only neutral terms. So a neutral term is either a variable. So if it's a variable, then I cannot apply the beta rule for function space here. And if it's a variable, then I cannot apply the beta rule for if then else, right? So these are the neutral terms, and the normal forms are, every neutral term is a normal form automatically, and we have lambda. So I don't know, let me write lambda x dot v is a normal form for any normal form. V is because I call it V because value is another name for normal form. And I just want a separate meta variable. And then we have true and false. These are also normal forms. Okay. So this is these will be the normal forms for a theory with only pi and bool. So more precisely, so in fact, there is a problem with this definition. Does anyone know what the problem is? Okay, so maybe it's a bit
maybe eta.
Yes, yes. So yeah, so there's only a problem if pi has eta. So if it has an eta law, then there are too many normal forms. Let's just see what are the too many normal forms. So for example, let's say we have an x, a variable x which has type in some context, okay, which has type pi a b. But we can construct another normal form, and then this x will be a normal form, right? Because x is a neutral term. Okay, let me be a bit more precise. Here I have some gamma, here I have the xab variable, okay, and then maybe I have some more stuff in the context. Okay, so x is a neutral term, and every neutral term is a normal form, so x is a normal form then, right? But I can construct another function which is equal to x, which another normal form which is equal to, which should be equal as a term to x. So I can just say lambda y dot of x applied to y. Okay. This is kind of the eta expansion of the same function, and these as terms, these are equal, but as normal forms, they have two different representations here, right? Because let's see how we got this. We started with the variable x, but then we were in the context where we also had a variable y of type A in the very end. So let me just construct it slowly. So x was the same as this. Now $y is in the same context. Okay. Sorry, let's, for dot dot dot, I just write theta here. Okay, that's theta is some end of a context. Then I write here x in a, y in a. Okay, and now I use lambda on this, so I get like something of this type, right? And these are equal because of the eta law for the pi type. But these have two different representations of normal forms, because here I just use this, then I included that neutral term in the normal forms here with n, and then I just use the lambda, which is this one, right? Okay, so we can fix this problem. So a fix is to disallow one step when constructing a normal form. So what we will do is we disallow this x to be considered, this neutral term. So this x is certainly a neutral term, but we will disallow it to be considered as a normal form unless it's of type bool. Okay, so this inclusion, so maybe the way to fix this is to add here some footnote, some star, okay, star footnote, and then the star says that we only include terms of type, or I mean neutral terms of type bool into normal forms. Okay, and then what I did, I ruled out this one. So this is not a normal form anymore. Sorry. So previously these were all normal forms. Okay, but now, okay, yeah. So now x is not a And then for that one, for that version of this where the star is here, I can really prove this. I can define this normalization function, and I can prove completeness and stability of this. Okay. Okay, so we've already seen this BNF grammar, so let's write it more precisely with type, because everything is typed even here. So the nicest way to define this is we just define it as an inductive type in Agda, say. So normal form of gamma A, and then it's just a set. And in fact, it's the nicest way to do it's a I just do it this way. Okay, so normal form gamma A, and oh, sorry, first I need, and then I also have neutral terms. So the neutral terms are, and these are defined mutually. Okay, so let me just write here all the constructors. So first I have variables. Okay, that's X. So if I have a var gamma A, so sorry, I also need to define variables. But every variable, I will define it in a second, is a neutral term. Then I want application. Okay, so application says that if I have a neutral term of type pi AB, and I have some V, which is a normal form of type A, then I get a neutral term at type B. But okay, this is not at type not of type B, because B is in gamma extended by A, so I need to substitute it with V. But wait, substitution is on terms and V is a normal form. So in fact, what I need to do is to define all of these strings at the same time as these inclusions. Okay, so I also need these inclusions. So I want to go from var gamma A to Tm gamma A and so on. Okay, and also for neutral terms. And no, sorry, I shouldn't have normal forms. Okay. And now what I can do is I take this value, I put it into a term, and then I substitute B with ID comma this one. And now this makes sense. Okay. And again, I have if then else, where given a neutral Boolean and two normal forms, any type, I get a neutral term of type A. Okay, so now I only write the non-dependent version, but you can also generalize this to the dependent version. Okay, okay. So what were variables? They were just de Bruijn indices, right? So we have a 0 de Bruijn index, which is just variable in A of type A, B. Then we have successor, which given a variable in gamma B, I get a variable like this, right? So I can put extra stuff at the end of the context. Okay, and you all know how to define these quoting back functions, right? Which go from variables, neutral terms, and normal forms to terms. Okay, so I finished with this part, and now let me just define these three elements. So we have a constructor for neutral terms, so it's the one with the star. So whenever I have a neutral term of type bool, okay, not any type, but of type bool, then that's automatically a normal form of type bool. Okay. And then I have lambda. So if I have a normal form in gamma extended by A, B, then I have a normal form in gamma of type pi AB, right? And this is just the quoting of this thing is just lambda in the syntax of type theory, and sorry, what else I have true and false. Okay, so true is just as it's a normal for a bool, and then I also have false, and that's it. Okay, so this is really an inductive definition, and you see again, just as for free monoids and for integers, there were no equalities when defining this. So this is a simple inductive definition. It's very simple to decide whether two such neutral terms or normal forms are equal, right? Because this is just an inductive definition. Okay, so it's easy to decide the equality of these normal forms, but you don't want to program with normal forms, because the point of programming is to write some program, and in the end you want to run it. And if you didn't want to run your program, then you could have written a normal form in the first place, right? So when we write programs, we want to write type theoretic, or when we write proofs, we want to write arbitrary terms, and not these severely restricted terms, because these are really restricted. Because, for example, on if then else, you can only apply it on a neutral term, or application, you can only apply it on a neutral term, and you cannot just apply it on a defined function which was defined by some lambda. But when we want to write nice, precise, nice short proofs or programs, we want to use defined functions in an application, right? That's the whole point of abstraction, to define functions and use them. Okay. Right, so these were the normal forms of type theory, and now, okay, so how do we do normalization? How do we normalize? And today I won't have time to describe how to do normalization. We will only do a special case, but let's see how we could attempt naively to do normalization. Let's just do induction on the syntax, okay? So can't we define norm as a function which takes Tm gamma A and returns NF gamma A by induction on the syntax, right? So that means by induction on the syntax. So that would mean that to define a model of type theory where contexts are just context, types are just types. So syntactic context, syntactic types, okay? And terms in this model should be normal forms, okay? Can't we do this? And then if we define all the rest of the model, as we did before at the previous meta theory seminars, we just said, oh, this is how you start defining the model, and you can finish it yourself. If I said that you can just finish this, it would be a lie. Why? Let's also look at substitutions. So a logical thing to say that what substitutions should be, substitutions are lists of terms, right? And now terms are normal forms. So maybe what we should have is to have they should be lists of normal forms. Okay, so NFs, and the NFs is easy to define. Let's just define NFs again as an inductive type. Data NFs is on arrow set. And then we have the empty NFs, which is in the empty context, and then we have, if we have normal forms from gamma to delta, give it some name, V's, okay, and then we can extend it with a normal form, okay. If we have a normal form which is substituted by the image of V's, and again we need to define this at the same time, right? Substitutions from delta, then we get NFs from gamma to delta extended by A. Okay, so this is how we could define this, and then we make sure that okay, contexts and types are the same as before, but terms and substitutions, they are normal forms, because that's what we want to obtain in the end. We want to obtain normal terms, and then having substitutions is just a step in between to obtain these normal forms. Okay, so now the problem is this one. So when we want to define this substitution, which goes from Tm delta A and the substitution from gamma to delta, and then we should obtain a Tm gamma of A sigma. Right? Okay, so before this, I also need to define a substitution of types, but that's easy because types are just types, right? So I can just I can just reuse the substitution of types. Okay, let's just do that first. So A substituted by some. Okay, so sub is now NFs. Okay, so A substituted by some V's. It's just the usual substitution of both of these. Okay. Okay, so now what about terms? So terms are normal forms. Okay, so this is now V's. It's NFs, and this is again a normal form. And here I need to use substitution of terms. So a substitution of types. So I get this one. Okay, so this is the function that I should be able to define. So now I need substitution of normal forms by lists of normal forms. Okay, but in fact, the problem is that to define this single function is as complicated as the whole normalization itself. Because let's say, yeah, so no hope here. Why? Like, let's say I have such a $X true. Okay, this is a term. And then I substitute it with some normal form where X is substituted by some lambda Y dot if Y, then something complicated else, something else complicated, then this will become, right? It will become, sorry, this one, applied to true. And this will trigger a lot more normalization, because you see here now I obtained a new red X. So I obtained a new, I obtained something which is not a normal form, right? This is not a normal form because only neutral applications are normal forms, and this is not a neutral application because a lambda is applied to some normal form. And I need to do lots of more equality checking when to obtain I need to go through lots of more equalities to obtain a normal form. So to do this, I already need normalization, right? Because I need to normalize this this dot 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 and this other dot 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 stuff here. Yeah. So I mean, okay, I don't need full normalization because these things here are also normal forms, right? So in this case, in fact, it should, because this one is a normal form here. Yeah, but okay, but I think it's quite easy to come up with more complicated examples where you see that it's not easy to do this at all. Right. So basically I need normalization just to define this. In fact, for simpler theories, there is some more or less direct way to define. So for simple type theory, for example, there's this hereditary substitution, which is some kind of more or less direct way to define this thing. But for type theory, we don't know of such a thing. But even for simple type theory, this hereditary substitution or the kind of direct way is much more complicated than the kind of normalization that we know about, which uses some different method. Okay, so here we say there is no hope. Okay, so failed. Okay, so this naive attempt failed. So let's look at the literature. So let's see how people do this stuff. And when we look at how people do this stuff, we would do it in 2 steps. So first, we prove a simpler thing, which is called canonicity, a special case of normalization. But the proof method is very similar. But the proof is similar, but simpler. And then we can look at normalization after we familiarized ourselves with this simpler case. And yeah, and the idea is, I think this idea is so it's also called some name. So it's called reducibility candidates, so-called logical relations, predicates method. In category theoreticians call this method gluing. I wonder if there are any other definition, other names for this. And it's a very old idea. I don't remember who came up with it, but I know where to look it up. There is Martin Löf talked about this at some lecture, and I think he traced it back very early. So maybe already Gödel used this method to prove something. But these days, it's, I think, the idea, and I think the guy maybe. So there is Tate, whose name is often mentioned or Tate's method. Yeah, so it's also called Tate's method. Okay, so this is names, and what is the idea? So the idea is that we cannot prove normalization by induction naively, just by stating, but by making, or by recursion, or just by stating that, I mean, when you want to do induction, when you want to prove something about some inductively defined set, such as natural numbers or such as the syntax of type theory, you can just say, okay, let's do a direct induction, and the direct induction is always just you put in your inductive motive. So what you want to prove, you just put your end goal, and then try to see if it directly goes through. And if it doesn't, then the general method is, then the next step is to generalize the inductive hypothesis. So try to prove something more general, what you wanted to prove. And maybe you can prove the more general thing, and then what you wanted to prove comes out as a special case. So this is like generalization of inductive hypothesis. Or, I mean, it's not really inductive hypothesis, it's the motive of the induction. So the motive is that of the induction, right, is what you want to prove. And okay, so we need to generalize. That's one thing. And then the idea is, for generalization, is that we don't prove normalization. So the statement of, so we don't say we obtain a normal form in the first place, but we say that this is called we define a predicate for each type. So we define a predicate for each type. So by induction on types, right? Induction on types. We don't do what we did here, that we leave types as they were, but we will, for each type, we will obtain a predicate, okay? And then for each term, we say that the predicate holds. And then when the predicate holds term of type not, say it should follow that the term, or sorry, let's say bool, it should follow that the term is a normal form. Okay, so this means in the case of bool that it should be the term, if it's in the empty context, then the term should be true or false. And the term should be true. Okay, so and these predicates, they are called logical predicates. So the names, so predicate is called logical predicate. It's also sometimes called by the thing that they express. So the predicate is also called normalizable, things like that, or reducible. So the predicate says that, so for each type, we say what it means, that its elements are normalizable. And then in the end, we prove that every term is normalizable. And because normalizable implies that it really is you can really normalize it, then we get normalization. Okay, so this was just some now it's very non-precise what I said. These are just the ways people talk about these things. But let's see a concrete example, and you will understand what this is about. Okay, so the concrete logical predicate. And this is for canonicity. So what we want to prove here is basically normalization in the empty context. Okay, so let's see what this says for our example type theory with these normal forms, so where we only have pi and bool. So here canonicity says that for any term in the empty context, so now we will only care about terms in the empty context, so we won't care about these general normal forms, but only about the empty context. If we have a term of type bool, then the t is either equal to false or it is equal to true. T is equal to true. And this is what canonicity says. So this is, I don't know, canonicity for a bool. Okay. And then we have another type. So we also have function types. So for function types, the canonicity won't really say anything. So pi AB, it just says that there exists some u, which is a Tm b, such that t is equal to lambda of u, right? So for bool, we get that a t is either true or false. For pi types, for terms of the pi type, we want to have that every pi type is a lambda, right? But in fact, this latter one is completely trivial. We don't even need this logical predicate method to prove this latter one, because we have eta law for pi type. So we know that we can always return up of t, right? And then here we need to prove that t is equal to lambda of up of t, and this is true by the eta law for pi types, right? Sorry, no, I should have put this here, right? So canonicity for function space is easy, and in fact, canonicity for canonicity for all types which have an eta law is easy. It just holds by definition, right? Like it's it's completely trivial, just like for function space or for sigma types. If we have sigma types, and if sigma types are defined with the eta law, so eta for sigma law types, it means that proj1 of t, comma proj2 of t is equal to t, right? This was the eta law for sigma types, and if you have this eta law, again, you can just prove canonicity by just because canonicity for sigma types would say that every term in the empty context of type sigma is a pair, right? And here you can always eta expand any term to be a pair, just like this. Okay, so okay, so now a question might come up. Oh, why do you even want to prove canonicity then? Why don't you just add eta laws? For example, we could also add an eta law for bool, and then this would be a consequence. So canonicity of bool would be a consequence of the eta law for bool.
Sorry, just one more question before.
Yeah.
Why don't we say that for sigma types, we require that it is a pair in which both sides are in their normal forms, or for a pair for which on both sides the canonicity holds. So like if it's a pair of bools, then the bools must be in their canonic forms, or why don't we make it stricter?
Because I think it's equivalent. So like look at natural numbers. That's even simpler. So for canonicity for natural numbers, it's enough to say that a number is either 0 or there exists some u, which is a natural number, and then t is equal to successor of u, and you don't need to require anything about u, because then because you have canonicity for every term in the empty context, right? You can just apply it to this one, so you know that this u is again 0 or successor. Okay. And the same here. So because you have canonicity for every term in the empty context, you automatically know that these two components are canonical. Sorry, where is it? Yeah, I didn't state it, but
okay, okay, thanks.
Okay, so in fact for Booleans, we could add an eta law, and then we wouldn't need to prove anything here. But then the more general normalization proof would become much more complicated, and also also it would be more complicated to. I mean, our standard interpretation wouldn't work anymore because we don't have the eta law for bools in Agda. So, and there's a reason for why we don't have a eta law for bools in Agda, and it's a bit because it's very inefficient. And then if you also wanted eta law for natural numbers, say, then eta law for natural numbers makes the theory undecidable. So makes equality undecidable. So you won't be able to define normalization at all in that case. So let's just stick to the theories that we discussed before. So ones without eta law for bool and without eta law for natural numbers. And for this theory, this canonicity is already interesting. And just if you think about this statement, this is not trivial at all, because this term of type bool in the empty context can be a very complicated term which uses application, lambda, if then else in multiple complicated ways, and and we have lots of equalities, but it's not completely obvious that we have enough equalities such that any term can be in the end rewritten to false or true. Okay, or any term can be equated to false or true, and this is what this canonicity says. Okay, so let's look at the canonicity model, and it is a displayed model. displayed model. So did we define displayed models before? I think when we discussed the family model, was it? Or I'm just wondering.
Yeah, I don't think so.
Okay, so I see, but I think we discussed displayed model before, but let me remind you what it is. So displayed, first simpler example, okay, just as you can do recur, okay, simpler example. So let's look at models and displayed models for natural numbers, okay? Algebras and displayed algebras, now that's a synonym. So, you know, a natural number algebra is some n set, and z in n and s in n are on. And the displayed natural number algebra over the, and okay, this is not algebra, right? And concrete one is the initial such algebra, so natural numbers with 0 and +1, right? That's one such algebra. And then what is a displayed not algebra over the syntax, over this? It is the data for induction, that we need if you want to do induction. So we have an n, which is a predicate on syntactic natural numbers. Then we have I should have written times here, but then this predicate holds for 0, and we also know, so that's the base case, and then we have the inductive case, and so we know that for any natural number, if the predicate holds for that natural number, then it holds for the number which is 1 greater than the natural number, right? This was, so I'm just talking about what we are interested here is that this is the notion of algebra or notion of model for a much simpler theory, right? Where you only have one sort and two very simple operations and no equalities. You compare this with the theory of type theory, which has 4 sorts, context, type, substitutions, and terms, and lots of more equalities, but it's the same principle. And this would be the corresponding thing to a model, and this would be a displayed model over the syntax or over the initial algebra. So when we define this canonicity model, we will also need a displayed model. And again, we have, so just as we have initiality, you know, which says that for any model, there is a morphism from the syntax to it. We also have the displayed version of initiality version, which is called, this is usually called induction. For any displayed model over the syntax, have a displayed section, or displayed morphism with. So a displayed model or dependent model is the. So there's a displayed version of morphism. So there's a displayed version of model, and there's a displayed version of morphism, which is usually called section. Okay, so now I know where we talked about all of this display stuff. We talked about this when distinguishing recursor and eliminator for inductive types inside type theory, right? So we discussed some we discussed what inductive types are in type theory, and inductive types come with recursion principle and induction principle. And now, when type theory is viewed as a kind of inductive definition, we again have the recursion principle, which is just for natural numbers. It would just be the usual recursion for natural numbers, or primitive recursion. And we also have the induction principle, which says that if we have a predicate and every operator respects that predicate, then the predicate holds for every term, right? So here what we will get, that and see how this matches our generalization of the induction hypothesis. So we define a predicate, and if every operator respects the predicate, then it holds for all terms, right? That's the idea. Okay. So now I just do it directly. So what is the canonicity displayed model? So the thing, we will have predicates for contexts and types, and for substitutions and terms, we will say that they are respecting a predicate, or the predicate holds for them. Okay, so what are contexts in this displayed model? It's a displayed model. So just as here n is defined as a predicate on natural numbers, here con will be defined as a predicate on syntactic context. Okay, so gamma is a syntactic context, and to distinguish it from context in the displayed model, I will write a prime next to syntactic things. So gamma prime, t prime, sigma prime are syntactic context terms substitutions. Okay. Okay. So here I will say that, okay, in the displayed model, in this canonicity model, every context becomes a predicate. Okay, and it will be a predicate on a syntactic substitution from the empty context to this gamma. Okay, and this is a predicate. So in this model, or in this display model, contexts become predicates, and also types become, okay, yeah, let's write types. So a type over gamma. Okay, now note that this gamma is a predicate. Okay, so gamma now has this type, right? Okay, I just write here. So A prime has type gamma prime. Then gamma is a predicate. And for types, what we say is that for any substitution, okay, any syntactic substitution from empty to gamma prime, if the predicate holds for this syntactic substitution, then it, oh yeah, sorry, no, sorry, what am I doing? Sorry, for types we want a predicate, so I just want, okay, sorry, I should have explained it differently. So I should have said that for types, A prime is a type in gamma prime, and we want a predicate on terms, but we only want to talk about closed terms. So we require that we have a closing substitution, and then we can talk about terms substituted by that closing substitution, so syntactic terms, and then we have a predicate over those. Okay, but we also require that the predicate already holds for this closing substitution. Okay, so we will only talk about predicate for types if the closing substitution, if the predicate already holds for the closing substitution. Okay, and let me just show you what the predicate will be for a bool. Okay, because we can already say that. So the predicate for a bool is so here we will need to have something of this type. let's see. So now bool is in the context gamma. Okay, so we'll have this type, and A is now replaced by bool prime. So syntactic bool. And we know that for syntactic bool, for bool, the substitutions don't make any difference. So basically, we don't care about what this substitution is. So for bool, I don't care about the substitution and that the predicate holds for it. Then it will be a predicate on booleans, and I say that this predicate for any boolean term in the empty context T will say what I exactly want. Okay. So that T is equal to false or T is equal to true. So now this is how I generalized what I wanted. So I was my original goal. And instead of saying that I prove this goal directly, what I will do is I just define this predicate for any type. And for bool, this predicate will say this. Okay. And now let's see how we define terms and substitutions and terms. Let's do substitutions first. So for a substitution from gamma to delta, where now gamma and delta are again these predicates on gamma prime and delta prime respectively. So they have this type. And now sigma prime is a substitution from gamma prime to delta prime, right? So okay, maybe I write this here for. Okay, so and I also have this, and now sigma prime is just a syntactic substitution from gamma prime to delta prime. Okay. Now what I say is I want to say that this sigma prime respects this, or this predicate delta holds for sigma prime. But the problem is that I can only talk about predicates in the empty. For substitutions in the empty context. So again, just like here, for types, I need a closing substitution. Okay, maybe for the closing substitutions, I call them row, okay? Or I use a different variable for them. Okay. So I will say that delta holds for sigma prime, but I need to compose it with some closing substitution. And just as here, I need to require that the predicate holds for the closing substitution. Okay. And then for terms, we basically say the same. We say that terms respect the predicate. So now we have a T prime term, and then we say that for any T prime is an arbitrary term. Again, T prime is some arbitrary term in a context gamma prime of type A prime, okay? But I in the end, I only want to prove something about terms in the empty context. So what I will say that I have a closing substitution, and for this closing substitution, okay, let's give this also a name. This is called row, which witnesses that okay, row hat maybe or something. So this is called row hat, which witnesses that the gamma predicate holds for row prime. And then I say that the predicate A holds for the term T prime substituted by row prime. Okay, and then here I need two more arguments, right? Because for every type, the predicate, we need to say what the closing substitution is. It is row prime, and we need to prove that the predicate holds for the closing substitution. So I need this row hat here. Let me just think a second. Okay. Okay, and okay, and before I can really, okay, I need to define the whole displayed model. I will do that, but let's just define the interpretation of empty context. So what is the predicate for the empty context? Predicate for the empty context is, let's see what its type is. This is its type, right? But now this gamma prime is empty prime, right? Or empty. Okay, so if I have a syntactic substitution from empty to empty, I want a set over it. But there's only one such syntactic substitution. So, and I say that for the empty context, the predicate holds trivially. Okay, so this is just the unit type. Okay, and let's see what I say for extended contexts. Okay, so now for extended contexts, this is the predicate. Now this is an extended context, gamma prime A prime. So I have a substitution. You know, a substitution into an extended context by the eta law for substitutions is an extended substitution. It has a sigma and the t component. And then I say that just as following the idea that substitution is just a list of terms, then this is the beginning of the list and this is the end of the list, and then I just say that the predicate holds pointwise. So I want the gamma to hold for sigma prime. Oh, sorry, this is sigma prime t prime. And I also want the A to hold for t prime. Okay, and here again I need to give the two components, because the predicate A depends on the closing substitution, and what is the closing substitution here? So, okay, here if you figure out the types, then you will note that this is just sigma prime, because this term it has a substituted type, so it has exactly this kind of type. So here I need to put the sigma prime, and here I need to put this first element, so this needs to be a sigma type. Let's call this sigma hat. Sigma hat. Okay, so basically now I just said, all I said is that, okay, for bool the predicate says exactly what I want. And then for empty context, the predicate is trivial. And for extended context, I just iterate the predicate for types. Okay. And now before showing the rest of the model, or for example, the interesting thing is how to define what is the predicate for pi types. Let's see how we use this model, how we use this model. So what we will get from any term Tm gamma A, so this is the induction for terms, right, or the dependent version of the unique morphism from the initial model, so from the syntax to any model. Now I have an induction principle which goes from any term to its displayed counterpart. I have that, let's call this from gamma prime and A prime. I have okay, I also have induction on context, gamma prime, and I have induction on types, and I apply it to A prime. Okay, this will be the induction for terms, but let's see a special case. So what happens if here I start with the empty context and bool? Okay, bool. Then here the induction on the empty context, which will return this one, right? So this is just, now I just write empty here, which is now this thing, okay? And induction on types will return this bool, right? This bool here. Okay, so I mean here this is the syntactic empty context and syntactic bool, and here I return the semantic empty context and semantic bool, and Tm will be this one, right? So replace this by this. So let me just, okay, so this is again the empty context, this is again the empty context, and this is bool. Okay. And let's see what these abbreviations are. So rho prime is just this. What is the empty context? I just said it's constant unit. So here I have an input constant unit. Top. And what is the relation for bool? It's this one, where I apply, where t is this. Okay, so what I get, in fact, is that t is equal to false, t substituted by rho prime, or t substituted by rho prime is equal to true. This is what I get in the end. Okay. And I mean, now you can see easily how you get canonicity, how we get canon, where it canon for bool. This is what I want. Okay, so let's define this now with the help of this induction. So canon bool of t will be, I use induction, I apply it to t, then I need to give a substitution from empty to empty. So let's give the identity substitution, right? It goes from empty to empty. Then I have element of top, which is tt, and now I get this. Right? This is what I obtain, where rho prime is the identity. Okay, but I know that I have the law that the identity substitution disappear, so I get t equals true or t equals false, and this is exactly what I wanted. Okay, so this is how it fits back together. So we try to naively prove this directly by induction, and that we didn't know how to do that, and now we use this idea of logical predicates, and we are able to prove it this way. Okay, and then so I showed you this bool, but now let's see how to define the rest of the model. So for example, we have a substituted type. So what is the predicate for a substituted type? I have a closing substitution for which the predicate holds, and then I just say I will use the predicate for A, and a predicate at A, and now I need a new closing substitution. But the nice thing is that I have a substitution which I can compose with the, I have the sigma prime, which I can compose with the closing substitution rho prime, and the predicate holds for the closing substitution rho prime. So I can use sigma, which says that sigma prime respects the predicate. So here I just use sigma, and on the closing substitution rho prime and rho hat, and this will exactly say that this composed predicate, this one, respects the substitution, respects the, so the predicate holds at this composed substitution at delta, and that's what I want for A. Oh yeah, and obviously I have a term t as well. So because where is it? It's here, because I have this t, and I can just put the same t here. Let's just check whether I can do this. So what's the type? I just copy this type here. So t here on the left hand side at type this one, where A is A prime substituted by sigma prime, right? Because A sigma, and here what I require is that here what I require is, again, sorry, where is it? It's this one. I copy and paste from here. Here I require something of this type, and rho prime is the closing substitution, which is now this one, right? So, and these two types again are the same, right? We have a law which says that for the functor law for type substitution says that these two types are the same. So these are equal. Okay, so this is how I do substituted types. And you know, I need to, when I define this displayed model, I need to check whether all the equalities hold. So for example, I need to check that AID is equal to A. Okay, so let's check this. So we need to check that this is equal to this where I don't use the ID. Okay. I cannot check it yet, okay, because I need to define the ID, so the interpretation of ID. So let's just do it quickly. So ID should have this type where sigma prime is replaced by ID prime, right? So ID of rho prime and rho hat will be just, oh yeah, and it goes to gamma, right? And we know that ID prime composed by rho hat is the same as rho hat, right? So this thing is the same as rho hat. So I just return rho hat. Sorry, it's the same as rho prime because of the left identity law. So the idea, so the interpretation of the identity, so the identity substitution in this displayed model is just the identity function. It just returns back the witness. Okay. So now I can use this definition when checking what this will become. I said that this is this. So this becomes this. So here, instead of sigma prime, I need to write ID prime, and instead of sigma, I need to write ID. Okay. But I know that this is equal to rho prime, and ID rho prime rho hat is defined to be rho hat. So just by definition, this is equal to this by the left identity law and this by the definition of identity. And that's what I wanted, right? Okay. So this is an example of the work that you need to do when you define a displayed model. Again, and it's just a generalization of defining a model, but there's always an extra dependency, right? So here it's a dependent function, and here there's always some dependency which you need to handle. Okay, and now we said that there's a predicate for each type. So we gave the predicate for bool. We gave what the predicate is for substituted types. So for substituted types, we just recursively use the predicate. So we just reuse the predicate of A and use the property of the substitution that it preserves the predicate. And let's see what the predicate is for pi types, because we haven't talked about that yet. So what are pi? What is pi AB? It should be a predicate over terms of the function type, right? B prime. Okay, so pi AB rho hat and some term is what? So for function types, we discussed that the interpretation of the predicate is not, so we don't really care what the predicate is as long as the induction goes through, right? So because here, where is canonic? So canonicity for function types didn't say anything. We already have canonicity for functions. For bool, we had to do some work, and we had to it was fixed what the predicate should say, but for function space, it could say anything. And then there are some you can derive, I guess, what this predicate says with some generic methods, but the people who define this, who use this logical predicate method for programming languages before, they said that for functions, what they want is that that basically functions need to respect the predicate. That's all they want to say. So if the and that's kind of the idea of this logical predicate method, that you when you for the base types, like for booleans and natural numbers, you put there the input which you want to say, which you want your predicate to say. But for functions, you just say that if the thing which comes at the input respects the predicate, then the output needs to respect the predicate as well. So for terms of the function types, if they respect the predicate, then the induction goes through. Okay, so this is what we will say here. So for any term u prime, which can be the input of this function, okay? So it's an input in the empty context, and of type A, where I need to use the closing substitution. If the predicate at A holds for this input u prime, okay? So here you see that I just reuse, because the input is also in the context, so A is also in context gamma, and pi AB is also in context gamma, so I can just reuse the rho prime and the rho hat, which are my dependencies. And I say that the predicate also holds at the output, so the output of the function is t prime, oh, this is t prime applied to u. And here I need to put my dependencies. So this is dependent function space. So B needs a closing substitution, which not only gives the gamma, so the rho prime, but an element of A as well, which will be the input itself, u prime. And now I need to show that for this extended substitution, the predicate holds. For rho prime, the predicate holds for rho prime because I have rho hat, and the predicate holds for u prime because I have this one. Let's give it the name u hat. And then I'm done. Okay. So for function space, I have that the functions respect the predicate. Okay, and you can check that this. So it's also similar. One more intuition for this is that functions are similar to like simply type functions are similar to substitutions, right? Where and dependent functions are similar to terms. So there's an input, and then there's an output which can depend on the input. So basically, what you see here is very similar to the interpretation of terms. So here you say that for any input for which the predicate holds at the output, and for terms we said the same. For any input, for terms, the kind of the input is the witness element of the context, so a closing substitution. Here it holds for the output, so the term respects it. So when I substitute the term with this closing substitution, for that thing the predicate holds as well. And here, instead of substitution, I have function application. So when I apply that term to an input, then the predicate holds for that at the input as well. Okay, and yeah, and now you can finish it. So you can finish it. So what is left? The operations lambda and application, and then okay, we haven't defined substitution for terms. The application, true, false, and if then else. Let's just quickly, these are not very interesting. Let's just look at true and false first. So for Booleans, this is what we say, that t is equal to true or t is equal to false. So for true, we will need to prove that true is equal to false or true is equal to true. So obviously we can prove that true is equal to true. And for false, we will need to prove the same, that false is equal to false or false is equal to true, right? And we can just use false is equal to false, and that holds. And then if then else is needs a bit more thought than this. So there we have a Boolean, right? About which we know that it is equal to true or false, because the predicate holds for everything. So it holds for this Boolean, right? And then we need to show that the predicate holds for this whole thing. But if the Boolean is true, then we know that if true, then something else is equal to something, and we already know that for that something is the predicate holds, right? So here we really needed to use, here we will need to use that the predicate holds for either true or so the predicate holds for the Boolean, and by that we know that the Boolean is either true or false, and by that we can rewrite our goals, so we will know that we will only need to show that the predicate holds for either this or this, right? So that's how this proof goes through for everything, and then we get canonicity in the end. And okay, so yeah, so that's all about canonicity. Okay, so let me just summarize what we talked about. So normalization, normal forms. So normal forms are usually given by an inductive definition for which it is equal to, for which it is easy to decide equality, and but it is hard for normal forms to it's harder to use normal forms, or to program with normal forms, or to reason with normal forms, and it is harder to define these general operations like substitute. And part of it, it's hard to define these general operations like substitution or general application for normal forms. But sometimes we want to simplify a program. Sometimes we want to know whether a number is 0 or not 0. Sometimes we want to know whether a Boolean is true or false, and that's when we need normalization. Or when we want to decide the equality of two terms, then we also use normalization. We can use normalization and these normal forms, and normalization returns normal forms from terms. And we saw that a naive attempt to prove normalization fails, and the more sophisticated attempt, we showed first a special case of canonicity or normalization. And the general normalization proof is very similar to this. It kind of follows the same pattern as this special case of canonicity. So once you understand this fully, it's more technical. So there are some more details, and it's because we have to. It's not enough to go from use closing substitutions so a substitution from the empty context, but we need to do it for arbitrary context and stuff. So it's more complicated, but the proof method is basically the same. There are just a bit more details there. So if you understand the canonicity version and you know the basic setup of the normalization version, you will be able to complete the normalization proof. Yeah. Okay, so the question is, okay, maybe I stop the recording, or are there any questions for the recording? Okay, then I stop the recording. No, sorry, I stopped the sharing for some reason, and I stopped the recording.